There we go. All right. So, well, today we're continuing on with energy, and well, last last time or last class or last day, we looked at a certain type of energy called kinetic energy, which was the energy that an object has because of its movement. All right. And today we're going to look at the second most typical or most, I guess, important energy, and that is gravitational potential energy, EG. So again, EG stands for E stands for energy, and G stands for gravitational. And that is the energy an object has because of its height. And so we have a formula for gravitational potential energy in which we have EG is equal to mass times G, which is 9.8, times height. Or because not all the time is an object starting from the ground level, we could just say it's kind of a same formula here, delta EG, which delta again in math and science stands for change. It's a Greek letter. But the change in gravitational potential energy can be considered again mass times G, but just times your change in height. So whatever amount that you've increased the height, whether you started from the ground floor or you're just changing the level, we have delta EG is equal to mg delta H. Now, as we looked at in our last day, the work energy theorem, in that when you put work into something, you're changing its energy, because work is the ability to transfer energy and do energy. We have example 1, which consider a box that's 20 kilograms being lifted from a shelf, from one shelf to another, I should say. Assume the distance between the shelves is just 50 centimeters, just like over in my diagram here, which again would be in standard units 0.5 meters. Find the work done moving the box. All right, so what we're looking at is our formula here for work is our force times distance. All right, now our force, when we look at it, is if we're moving at a constant velocity, as you see I have labeled here, well, there is a force down always, the force of gravity acting on the object. And to move it at a constant velocity, we would have to have a net force. And so a net force of 0. And so that means that our applied force and the force of gravity are equal in magnitude, but of course opposite in direction. And so I can replace my force in this F times D with mg. So our force is now mg, mass times gravity, because that's the force of gravity. And instead of having a D, well, it's really an H, because our distance is straight up, which of course we call our height. And so if I substitute those values in, I have our mass here of our 20 kilogram box. Again, G is always 9.8 on Earth. And our change in height is 0.5. And if I multiply those three values, I get 98 joules. And again, the point here is, just like the other day, is that the work done to increase the elevation of an object is equal to its change in gravitational potential energy. Where the other day, the work was created a change in kinetic energy, a change in speed. This time we have a change in height. All right, so then we get to example 2, for example, a gas-powered winch on a rescue helicopter does 4,200 joules of work while lifting a 50 kilogram swimmer at a constant speed up from the ocean. Through what height was the swimmer lifted? All right, so looking at our values that we have, our work that we're applying is equal to our 4,200 joules. Now, the mass of the swimmer that we have here is 50 kilograms. And of course, our G value here is 9.8. All right, meters per second squared. I'm just going to leave that out, though. Now, what we want to know is the H value of how high up was this person lifted. Now, again, in this situation, the work of the winch, in this case, is increasing the gravitational potential energy It's changing it. Actually, it's from 0 because this person is in water, which again would be mgh. And so I can substitute in my values, in which case our work, again, we know it's 4,200 joules of energy. The mass of this person is 50 kilograms. They're on Earth, so G value is 9.8. And we can find their height, that they're increasing. But in this case, it is their height because they're starting from, well, ocean level or sea level, we should say, I guess I could say. All right, so just simplifying here, I have my 4,200 joules. I take my 50 times 9.8, in which I get 490 times H. And of course, to get my H value by itself, I'm going to divide both sides here by 490. And let's see here. Our H value, if we take 4,200 and divide it by 490, this person has been lifted up. It's about 2 or 3 stories, actually, maybe 4 stories, 8.57. And again, because we're in standard units, meters. All right, so again, the work by the winch increases the gravitational potential energy of our person who needs to be rescued. Now, something that we're going to get into, or it's going to be a huge application of what we've been doing, is what's called the law of conservation of energy. And what the law of conservation of energy says is that when energy changes, because we've talked about energy being applied, work being done on something, but sometimes there's no addition of energy, it's just changing. And when energy changes from one form to another, here's the key, it's conservation. So no energy is lost or gained. All right, so no energy is being added here, we're just changing forms. Now, another definition here is what we call mechanical energy, EM. I don't know why they come up with this name. Usually math and science people are pretty boring when they label stuff, but I have no idea. But mechanical energy is simply the total amount of all the energy in the system. All right. So for example, example 3 here, we have a 14 kilogram piece of dead wood falls from a tree from a height of 23 meters above the ground. Cannot calculate the kinetic energy of the wood as it hits the ground. All right, so we did kinetic energy last day. Now we've got gravitational potential energy. Now in this situation, we want to calculate our kinetic energy, all right, when it hits the ground. We know the mass of the object is 14 kilograms. There's our M. All right, our initial height here is 23 meters. Now, in this situation, what is happening is that the tree starts off at a certain height and it has a bunch of gravitational potential energy. Now, what happens is all that gravitational potential energy is then going to be converted into kinetic energy. Because no energy is lost, they are equal, because when it hits the ground, you have the piece of wood no longer has height, and therefore no longer has any gravitational potential energy. And so our gravitational potential energy at that height is mgh. All right, and it is going to be converted into kinetic energy, which we looked at as mv squared divided by 2. All right, so what I can do is substitute in my values. So my mass of my wood is 14. Actually, we're just trying to find the gravitational potential energy here. So let's erase that and let's put in EK. All right, so all our gravitational potential energy is being converted into kinetic energy. And so I have mass times my 9.8 times the height, and this branch is falling from a 23-meter height, all right, is equal to EK. And so if I multiply my three numbers, let's see what I get here. 14 times 9.8 times 23. I end up with, and again, go to two decimal places, 50, I get 3,155.6 joules of energy. So that's what we not only have at the top, but as gravitational potential energy, but when it hits the ground, that's what the same amount of energy is there. Because again, when energy changes, in this case from gravitational potential energy to kinetic energy, nothing's lost. All right, so this is the energy at the top and also at the bottom. But now calculate the speed of the wood as it hits the ground. All right, well, again, here's our kinetic energy that we have at the bottom. And so that kinetic energy, again, from the other day, our EK is equal to mv squared divided by 2. And so what we have is we do have our 3,055.6 joules of energy, which then is equal to, again, the mass of our wood is 14. And then we have v squared. And of course, I can't forget the fact that this is going to be divided by 2. All right, so I can keep going here and just simplifying to solve for our v. So I have 3,155.6. Well, 14 divided by 2, I know is 7, times v squared. All right, again, simplifying here, I can divide both sides by 7. And so I end up with, I take 3,155.6 divided by 7. I get, let's see here, 450.8. And that is going to be equal to our v squared. All right, and of course, the last step is to take the square root of both sides. And I get v is equal to, let's see here, I'm thinking 20 something, but it could be wrong. 21.23 meters per second. So again, that is all our gravitational potential energy converted to kinetic energy. All right, because again, conservation of energy, no energy is lost or gained because we didn't put any work in here. All right, let's try another type of one of those. Is that we have many roller coasters. Roller coasters have loops where carts roll on a track that curves sharply up in the air. Always my favorite here. So this one here, to be honest with you, is Canada's Wonderland, the Dragon Fire, first one on the right when you go into Canada's Wonderland, which hopefully we can do someday. Now, in the roller coaster shown, which is, I'm going to say 500 kilograms, the cart must have a minimum speed at the top of the first loop of 10 meters per second to make it around safely here. All right, so we got to have a velocity right here. Well, we'll get to this. Assuming the roller coaster starts from rest at the top here of the first hill and there is no friction on the roller coaster, what is the minimum height of the first hill? All right, so again, I got some values here I'm going to write down. Situational stuff. Again, the mass here is 500 kilograms. All right, the minimum speed that we need at the top, we got to have 10 meters per second to get around. All right, because what a lot of people don't realize in a roller coaster is that all of it is just converting gravitational potential energy here at the top, e.g., all right, we don't know how much, all into, there's constantly an energy transformation. There's no motor on a roller coaster. It's all physics. They pull you to the top and they let you go, and you need enough energy to get all the way around. So it's important to, know your heights and your speeds. Now, in this case, we're going to start off here with, this is, I guess, our spot number 1. And here's spot number 2. All right, so all the energy in spot number 1 is going to be gravitational potential energy. Because again, our velocity at the top, it says that, well, we're just at rest. All right, so, which is kind of true, right? Because when you get to the top of a roller coaster, if you've ever been on the front, you're barely moving until you get right over the top of the hill. All right, now that's going to be converted to our second spot here, in which we have two things. We have height, so I guess EG2, this EG1, plus we're still moving. So we also have kinetic energy. Now, our energy is neither lost or gained. And so the energy we started off with at the top is going to be equal to this energy that we have at the top of the first loop. All right, so what does that look like in terms of our values? Well, we have EG1, so I'm going to call that, we have mass times G times our first height, which I guess I'll call H1. Now that's going to be equal to, we have gravitational potential energy again, which we have mg, but times height 2. But we also have kinetic energy. So I have mass times velocity squared. Again, that is going to be divided by 2. All right, so what we're looking at here is we want to know H1. That's our big question here. All right, so I'm going to now substitute into my values. I know my mass here is 500. We're on Earth. That's 9.8. All right, let's see, H1, that's what we're trying to figure out here. Equals, let me see. Now, again, we have mass 500. G is 9.8. And H2, we have a height 16 on that first loop. Plus, we have our kinetic energy. Extend this out. Where we're going to have, again, 500. We need to go a minimum speed of 10, it says. So we're going to have a 10 squared. And then, of course, we got to divide it by 2 here. All right. So, as you can see, we got everything we need. We just need to know H1. So I'm going to do a little bit of math here, simplifying 500 times 9.8. That should be a nice round number, I think. And it is 4,900 times H1. All right, and that's going to be equal to, let me see, I multiply those three numbers, 500 times 9.8 times 16. I get 78,400. All right, plus, now I got to make sure I follow Bedmas here. Do the exponent first. So 10 times 10 is 100. Times 500 is 50,000. Yeah, and then divide by 2 is 25,000. All right. Again, just simplifying things. Whoops. So we got our 4,900 times H1 is equal. Let's put those two together. It's going to be 100,000. Let's see here. We get 103,400. All right. And then, of course, the last step is that we're going to divide by this 4,900. And it turns out, let me see here. I take 103,400 and our height value here that we need on the top loop is 21.1 meters needs to be the initial height of our roller coaster. Now, again, that is somewhat of a simplified version of how a roller coaster works, but there's not much more than that other than they have to account for friction and heat loss and different things like that, and a certain percentage because you can have wind resistance. But in the end, a roller coaster just simply works on the law of conservation of energy, in which case energy is neither lost or gained.